Hi, welcome to the elasticity class. Today we are going to talk a little bit about how to do basic vector operations in various coordinates. This is very important, especially vector calculus. So that's why we are trying to do this. One of our basic tasks is to do things like divergence, curl, gradient and all of that for various vectors. So we should be familiar with how to do it. Before you do it, there are three websites that I ask you to go and take a look, and I have listed them here. And if you cannot see the three websites, I'm going to zoom in a little bit and maybe you can see which websites they are. Hang on, give me a second. There, can you see those three? All of them are from YouTube, and I could tell you that by far they are some of the best core explanations of what is meant by divergence and gradient and curl and all of this. So I would strongly urge you to take a look at those three websites because they have beautiful explanations. Okay, so I'm assuming that now you have seen what is meant by divergence, gradient and curl and all of that. Now we are going to go ahead and figure out how to actually calculate it. The starting point for it is we are going to do this in Cartesian coordinates. So basic procedure is 1. Choose coordinate system. 2. There's something called figuring out line element. Third thing is then use appropriate calculation. I'm not going to tell you how these things are derived, these particular calculations are derived in detail. I'm going to give you only a vague idea. If you really want to learn how to do this, this is a whole area called exterior calculus, which is a beautiful area of differential geometry, and I would strongly urge you to take a look at it if you are interested. If you just want to use this, what I'm going to tell you will give you enough background to get you into trouble. Okay, you know what I mean, right? So, so that's the idea. So in Cartesian coordinates, our first coordinate system is Cartesian coordinates, and we know what they mean, right? I have the three coordinate lines, or the x lines, the y lines, and the z lines, right? And any vector R looks very simple, xi plus yj plus zk. And since I want to write things in compact form, I'm going to rewrite it as x1i plus y1j plus z1k. Sorry. Oh, I'm sorry. I should have put it as x1i plus x2j plus x3k. So it's convenient to write it this way. So then what happens is I can show you, for example, that this is a trivial and boring thing, but later will turn out to be useful. If I differentiate r with respect to x1, I'll get I. And if I differentiate r with respect to x2, I'll get j. And if I differentiate r with respect to x3, I'll get k. You're thinking, what's the big deal? And there's no big deal here. But I want you to figure out that therefore I is the tangent to the x1 line. That's the tangent to the x1 line. J is the tangent to the y line. And k is the tangent to the z line. Okay, that's how it works. Excellent. So once we get that, now I can talk to you about line elements. So what happens if I increment r slightly? So if I want to calculate dr, okay, that's pretty easy. That will turn out to be increment the x a little bit, plus increment the x2 a little bit, plus increment the x3 a little bit, which I am going to write it like a column vector, dx1, dx2, dx3. It's time for us to do some notation. So we're going to use very specific things. So if I put like that, that's a row vector. If I put like this, that's a column vector, and if I put like that, that's a matrix. Okay, in fact it's kind of a square bracket with curved ends, but you know what I mean, right? So those are our three notations: row vector, column vector, matrix. And this will be when I write down multiple matrix equations. Of course, you know, I may sometimes use this for grouping terms and things like that, so don't get confused by that. Okay, so that's our idea. So I'm going to write this as a column vector. Very good. Now first up is gradient, and the idea behind a gradient is that if I go from point A to point B, okay, and I look at some function f, so fb minus fa is approximately equal to gradient f times b minus a, if a and b are close. We are going to formalize this idea. The formalized idea will tell you that df, that is fb minus fa, is a vector which is equal to gradient of f, which I am going to write like that, times dr, which I am going to write it as a column vector. Let's see if that makes sense. So let's see. Suppose I give you f equal to f of x1, x2, x3. So what's df? You know how to do this, right? This is just chain rule. So that will give df dx1 dx1 plus df dx2 dx2 plus df dx3 dx3. I think what a big deal. No problem. This we will write it as df dx1 df dx2 df dx3 times dx1 dx2 dx3. Notice that was this. So this is dr and this is gradient of f written as a row vector, and we will write it as gradient of f, gradient of f equals df dxi ei summation over I, where e1 is I, e2 is j, e3 is k. That was easy, right? This is a very important one. We will have later occasion to use it. For example, if f is x1 cubed plus 3x1 squared x2 plus, x2 squared plus 4x2 sine x3, then gradient of f, let's see, will be differentiate with respect to x1, and you will get 3x1 squared plus 6x1 x2 squared. This is in the e1 direction and e1 was I, so that's I, plus differentiate with respect to x2 and you will get 6x1 squared x2 plus 4 sine x3 j plus differentiate with respect to x3 and you will get 4 x2 cos x3. That was no big deal, right? So that's how we compute direct divergence and so on. So gradient. Now we are going to look at a second example. In this case, we are going to look at a vector v, which looks like v of x1, x2, x3. And in our particular case, let us say v equals 6x1, x2 I plus 7x1 squared x3 squared j plus 8 x1, x2, x3. There's some made up stuff, so don't worry about what this means. It's just some field. Okay. So first up, we want to be able to do divergence. So divergence of V. Remember what the heck divergence was? Divergence of V is defined as limit of the volume tending to 0 of integral V dot dA divided by volume. What the heck does that mean? If you imagine V to be the velocity of a fluid, this is net outflow divided by volume. That's what divergence. So it's the net outflow per unit volume. That's what divergence means. Divergence of V equal to net outflow per unit volume. That's the meaning. How do we compute it? There are a couple of different ways. Our method, and I'm going to tell you actually only the answer, I'm not going to really belabor the point. Our divergence is given by summation df dxi, dv dxi dotted with ei. I equal to 1, 2, 3. So this turns out to be, in our case, V1, and we are going to use a new notation. If I put comma 1, that means d dx1. Something comma 2 means d dx2. Something comma 3 means d dx3. Okay, so if you know that, that will help you. So it will turn out to be V1 comma 1 plus V2 comma 2 plus V3 comma 3. This is easy because if you remember, our V looked like that. So I'm going to take that and use this here, and I will get, I'm going to take that, use this here, and what will I get? I will get V1 comma 1. So 6 partial with respect to x1 of 6 x1 x2 plus partial with respect to x2 of 7 x1 squared x3 squared plus partial with respect to x3 of 8 x1 x2 x3. That's easy, right? There's nothing to it. Immediately you will get, so 6x2 plus 0 plus 8x1 x2. So if you pick a point, so let us say you pick 7 comma 3 as 7 comma 3 comma 0. This is x, this is y, this is z. Then the net outflow per unit volume at 7 comma 3 comma 0 is 6 times 3 plus 8 times 7 times 3, which is, let us see, 6 is 18 plus 7 8 are 56 times 3, 56 times 3, 60 is 18, 8 1 5 3 is 15, 16, 168, that is 186 units of outflow per unit volume at the point 730. So at each location, by looking at the divergence, you can figure out how much material is flowing out per unit volume at that location. That's what divergence means. Very good. So, and our formula for divergence in Cartesian coordinates looks very nice. Take the first component of V, differentiate with respect to x1. Take the second component of V, differentiate with respect to x2. Takes the third component of V, differentiate with respect to x3. Excellent. Now let us look at curl of V. So again, if you go back, curl of V was net circulation per unit area. And why is it a vector? because there are three kinds of unit areas, right? There is, this is the unit area, this is the component of curl V. First component tells you how much is the circulation around this cube. The circulation this way is the first component of V3. The second one is the circulation this way. This will give me curl V, second component. Third component is the circulation that way. So that will give me curl V, third component. So this is the Z component, this is the X, and that's the Y. So that's what it means. On the three faces of the cube, how much circulation is going on? That's really what curl of V means. How do we compute it? I'm not going to write all the steps, but I'm just going to show you how to do it, because that's really what we are after, curl of V. So what we're going to do is we're going to write it as determinant of the following matrix: I, J, K, partial with respect to x1, partial with respect to x2, partial with respect to x3, V1, V2, V3. Pretend it's a determinant and just compute it. Okay, this is the best way to compute curl of something. Turns out to be beautiful, very nicely extendable. So please pay attention. This is the best way. All this, forget about all this, doing this del cross and all this, it will not work out well. This is the easiest way to do it, and it will work beautifully for many other cases. So in our case, this is I, J, K, partial with respect to x1, partial with respect to x2, partial with respect to x3, and then we have, what was our, you remember our this one, it was 6 x1 x2, and then we had 7 x1 squared x3 squared, and then the last one was 8 x1 x2 x3. Right? So compute the determinant of this. So we are going to do a row wise expansion, that is I times do 8 x1 x2 x3 to x2 minus do 7 x1 squared x3 squared to x3 plus the other two things. You know how to expand by determinants, right? The row expansion. If you don't, time to find out, please. You know, I cannot teach you everything. Some of the things you have to learn. So please go and find out how to do row expansion to calculate determinant. Okay, very good. So I'm going to do this. This turns out to be I times, well, differentiate this with respect to x2 and I'll get 8 x1 x3 minus 14 x1 squared x3 plus j times, you should know how to do this, 0 minus 8 x1 x3, sorry, 8 x2 x3 plus k times, differentiate that with respect to x1, 14 x1 x3 squared minus 6 x1. That's curl. So this is the circulation around the x-axis, this is the circulation around the y-axis, that's the circulation around the z-axis. Okay, that's what curl means. You got the idea, right? If you have trouble going from here to here, you go find it out. I'm not going to sit there and explain that to you, please. You know, you got to learn. Okay, very good. Last up is gradient of a vector. So again, what we are going to do is, we are going to do, given a vector v, which is v1i plus v2j plus v3k, I want to be able to find dv, right? And that turns out to be dv1i plus dv2j plus dv3k. I want to package it in a very nice way. So we know how to do dv1 because that's just gradient of a scalar. So we know how to do that. So we are going to do this as gradient of v1, right? That's dv1 dotted with dr times I plus gradient of v2 dotted with dr times j plus gradient of v3 dotted with dr times k. That was easy, right? So now we are going to write this in a nice way. This I am going to write it as a column vector. Gradient of v1 dotted with dr, gradient of v2 dotted with dr, gradient of v3 dotted with dr. That's nice. I'm going to factor out the dr and I'm going to write this as a nice matrix. Gradient of v1 here, gradient of v2 here, gradient of v3 here. These are all scalar, just gradients of scalars. That's all you have to do. Times dr, which is dx1, dx2, dx3. So if I write this as a row vector, then we are done. So this looks very nice. It looks like v1 comma 1, v1 comma 2, v1 comma 3, v2 comma 1, v2 comma 2, v2 comma 3, v3 comma 1, v3 comma 2, v3 comma 3. This generally sometimes this is called the Jacobian of the vector, and this is dx1, dx2, dx3, and this, by the way, is called gradient of v. And now you have e1, e2, e3 going this way and e1, e2, e3 going that way, because the first component goes e1, e2, e3, the second component goes e1, e2, e3, like that. Okay, so we are going to write this in a very compact notation. Gradient of v equal to summation over I, summation over j, vi comma j, ei ej. This tells you where it goes. This tells you value of the compound. What do I mean? What v1 comma 2, e1, e2, where will it go? First, the value is v1 comma 2, that is dv1 dx2. Where will it go? It goes in the first row, first column, second row. First row, second column. Excuse me, I'm very sorry. First row, second column. So first row, second column, it goes here. So this tells you row, this tells you column. Okay, so let's do it for our case. Gradient of v, the matrix will look like what does our matrix look like? v1 comma 1. Remember, v was 6 x1 x2 I plus, I want to make sure you got the right numbers, 7 x1 squared x3 squared j plus 8 x1 x2 x3 k. So this is v1, this is v2, this is v3. So if you do this, you will get v1 comma 1 6x2 here, v1 comma 2 6x1 here, v1 comma 3 0 there, v2 comma 1 14 x1 x3 squared. v2 comma 2 is 0, v2 comma 3 is 14 x1 squared x3, and then the last one will be v1 comma 1 8 x2 x3, then 8 x1 x3, then 8 x1 x2. If I want to write it in this kind of notation, this will look like this. That is equal to 6x2 e1 e1. e1 means first row first column, plus 6x1 e1 e2 first row second column, plus there is no point in writing, there is nothing there, then 14 x1 x3 squared e2 e1 second row first column, plus 14 x1 squared x3 e2 e3 second row third column, plus 8 x2 x3 e1 e3 first row third column, plus 8 x1 x3 e1 e2 first row third row first column, third row second column, plus 8 x1 x2 third row third column. All the others are 0. So this is an alternative way of writing, and there are certain uses to it because it tells you which coordinate system I am using. In fact, I should have put I and then I have put ij, so it will immediately people will know ji, then this will be jk, and this will be ki, this will be kj, and this will be kk. So you can actually replace it with the appropriate notation. Some people will not only do this, they will also write it as E1 tensor product E1, like that. This is called a tensor product. This just tells you I am doing, instead of doing dot product, which is row times column, they are doing column times row. Right? Got the idea? Excellent. This is how we compute gradient of a scalar, divergence of a vector, curl of a vector, and gradient of a vector in Cartesian coordinates. We are now going to do the same thing in other coordinate systems, and that will be the content of our next couple of lessons. Thank you.